B part 4, lecture 28, classical mechanics, spatial translation, Noether theorem. Today is May 10th. Now, consider two particles, M1 and M2, belongs to the space, Euclidean space R3, moving with the velocities v1 and v2. The kinetic energy is defined, for these two particles as is written over here. You see, this is a position vector, and that's or the particle 1 and then the particle 2. That's kinetic energy. And the potential energy, attention now, potential energy depends on the distance between the particles. So this is R2 minus R1 dot R2 minus R1, the square root. So it's V. You see that's a distance D. This is D square. You look at here, this case, position vector R1 and R2, and D is the distance between the two particles. So again, I just substitute here this dot product. This is R3, this is X, Y, and Z. This is the basis vector for the Euclidean system coordinate. So this potential energy, you see, this is squared, the distance. That's the square root of d square. This is d square. So V1, attention, is the first ordinary derivative of the vector position, or the position vector R1, and this R2. This is R1 dot and R2 dot. Is the derivative respect to the time. Attention. Here, the time is not explicitly, you see, but the time, belongs to this position vector here, because this particle here you move, but spatial translation means that this distance doesn't change as the particle moves. You see, that's the definition of the spatial translation. So let's apply a translation. You see, R prime 1 is R1 plus this epsilon, this is a vector, So R prime 2 is R2 plus the same here, the same vector displacement. That's a teeny displacement, you see, which in this case is assumed as constant. So this vector over here is assumed constant. So just this can be expanded, throughout the components, the coordinates. This x prime I, xi plus xx. Here it's important here that I here represents or 1 or 2. You see, because we are dealing with two particles only. You could, extend for many particles, any particles, for instance. So since this vector, this teeny displacement is constant, the dot of the space is equal to 0. So this implies, attention now, that the dot of x prime I is equal to the dot of xi. This because epsilon dot is 0. So the same, likewise, z prime I is equal to I. Again, I can be or 1 or 2. See? So this leads to the kinetic energy, T prime depends on the time is equal to T. So there's a consequence. Now, on the other hand, see, the potential energy square, you see, if you take the dot product of R2 minus 1 dot R2 minus 1, this will lead exactly what's written over here. You see? So this, and also this case, if you apply this R2 minus R1, see, just leads to this square over here. And this is x2 plus epsilon x minus x1, you see? This over here is x prime, this is prime, you see, minus this is prime. So this x 2 prime, this x 1 prime. You see, I just substitute from this sum over here. And likewise, this one, you see, this here is y prime 2, and this over here minus y prime 2, this is 1. See, that's substitute and you see. So, attention now. This over here cancel with this. And this one you cancel this. So this leads to, in this case, the same x2 minus x1 plus square plus y2 minus y1 and z2 minus z1, which is the potential squared. Now just take the square root, you see, then this leads to the potential energy. By definition, see, the Lagrangian, okay, is kinetic energy minus potential energy. You just substitute and see that L prime of t, you see, this is t prime minus v prime, which this here, just you substitute, is the same as t, and v prime is the same as v. So this difference remains the same. That's why the Lagrangian, okay, when you move, the spatial displacement, okay, spatial translation, the L prime doesn't change. That's very important here. Now, I'll call attention this is for the time t fixed. You see the time t, you see, is fixed. Attention now, time t is fixed. You just displace, you have the displace. At the same time, okay, there is a spatial translation, the same time. Now you consider now, okay, this displacement vary with the time. That's the next what you develop here. You see, moving particles. You see here, look, moving particles. Let us change notation and work with only one coordinate for more clarity. You see, instead of I work with x1, x2, x3, oh, I'm sorry, x1, in this case, x2, and y1, y2, and so on, I just pick one, just one over here. So this is as I show here, you see, I just pick one direction, okay? This I call x. So instead of working it's x, y, and z over here, I just work with x. And then in the final, I can write the full expression. So that's very, very easy. So, attention now, for more clarity. x1 of t is x bar of t. I change notation. It's the same value, okay? I just set a bar over here. Likewise, the x coordinates of the particle number 2, you see, is just x bar x2 of t. Assuming, this is important, assuming the tiny displacement, you see that's the direction that I'm choosing to develop, okay? I'll not develop for x, y, and z, I just for x. This is particle 1 and particle 2. You see, the motion, okay, depends on the time now. So, x bar 1 of t, okay, is x bar 1 of t plus this displacement over here. You see? This is epsilon. Likewise, x2 bar, okay, is x2 at t plus a tiny displacement. You see, this is the displacement. You see? There's a wiggling motion, okay? That's teeny, very, very small displacement. Now here, you see the time is moving. See? Attention now, what's confused. You see, the Lagrangian could be expressed with the time explicitly, but in this case, the times only appear, okay, in the position vector r of t. You see, this is which we calculate the velocity. You see, that the time is varying, okay. So the time at the point, okay. This time here is not explicitly in Lagrangian, okay. That's I called attention many times in previous videos about that. So now consider now the action. See, the action S. You see, function of x bar. Attention now. This x bar here is the same of x1 here, x1, x2. In this case, y1, y2, z1, y. The same. You see, it's identical. Okay, I just changed the notation as I mentioned just over here. You see, so the action is integral from t1 to t2. Now the particle is moving. You see, now x bar t, x dot bar. In this case, the velocity here dt. That's